My name is Kinan, and I'll be talking to you today about our new batch differentially private peer protocol. This is joint work with Rawane, Mayank, and Kalman. So private information retrieval, or peer for short, is a cryptographic technique that allows users to query a remotely held database while keeping the contents of their queries private and unknown to the service. Peer protocols generally rely on encrypting, secret sharing, or otherwise obfuscating these queries and their responses. The service here may consist of a single server or many servers, and we're going to focus in this talk on the multi-server setting. Peer is a powerful primitive with endless potential applications, and researchers have developed many peer protocols and proposed using them for a variety of applications. I'm showing only some of them on this slide. A highlight of existing work is the offline-online model, which uses a per-query pre-processing stage that performs expensive operations offline to speed up the online protocol. However, peer hasn't seen really much adoption in the real world, and one natural question is why. We believe that this is in part a challenge of scale. Peer has known lower bounds that prove that significant per-query overheads are required to provide privacy. This makes peer scale poorly to large query loads, as we will see next with a potential application. So in this example, peer application, let's imagine a service that keeps a database of vulnerabilities, and they're found in different software dependencies and versions. Proprietary software developers can query this service periodically using peer in order to ensure that the dependencies are safe, while at the same time keeping sensitive information about their dependencies and potential vulnerabilities private. The challenge here is in the scale. We know that there are millions of dependencies available on repositories such as NPM or Maven Central, so the database has several million elements. The total number of software projects that may use the service is in the hundreds of millions, each with tens of dependencies. So if every project is going to query for the dependencies once a day, that gives us about billions of queries daily. So can peer constructions scale to such loads? We'll look at this we'll look at the performance of Checklist, a state-of-the-art two-server protocol that uses the offline-online model. This is a very recent protocol from last year's USENIX security. And what we're going to show here is only the online cost. We're not going to show the offline cost. Our database size, which we denote by n, is 2.5 million elements. And we ran Checklist's code on Q queries, which we show on the x-axis, and measured the online time required by the servers to handle all of these Q queries in seconds. And we report that on the y-axis. Both axes are log scale. The computation complexity in Checklist is in the order of square root n per isolated query. This is pretty good for peer, since that level of server work is generally required for privacy. However, Checklist handles every one of these queries separately. So it has to pay the square root overhead for each query, which means that for Q queries, the total computation time is in big O Q times square root n. For an application like the software dependencies one we looked at, where the service needs to handle billions of queries daily, the per user per query overhead in Checklist compounds and makes the total cost impractical. On our setup, it takes us more than a day to perform the server-side computation for these billion queries. This gets even worse for larger database sizes because of this multiplicative dependency on square root n. Due to the theoretical lower bounds for peer, there is very little we can do to improve the asymptotic complexity of any isolated query. Instead, applications like this one with a large number of queries give us an opportunity to amortize the overheads over the different queries. This requires us to handle queries in batches rather than individually, but poses an interesting challenge. We need to amortize costs over the queries made by different users, while also carrying out the expensive operations offline to speed up our online protocol. In this talk, we present DP-Peer, a new multi-server peer protocol for applications with many queries. DP-Peer batches and amortizes the costs of queries made by different users down to a constant. Our protocol processes a batch of Q queries in big O of Q plus n, and it relies on a new secret sharing scheme in order to move all public key operations offline and use only cheap arithmetic operations online. I'll briefly discuss the sharing scheme later. At a high level, DP-Peer combines three techniques. First, we reveal a noisy histogram of all the queries to the service. This protects the queries of any given user with differential privacy, and we intentionally accept this leakage in order to provide good scalability. Second, our protocol batches the queries from the different users and shuffles them using a mixed net design. And finally, we move all expensive public key operations to an offline stage, which can be carried out during off-peak hours, so that our online stage uses only a few arithmetic operations per query. For presentation purposes, I'll show a simpler construction that uses only the first two techniques, but carries out all operations online, including the public key ones. And I'll briefly discuss how we do this online-offline design afterwards. Our setup consists of many users that query a remote service, and this service consists of 2 or more servers structured in a chain. Our protocol tolerates a malicious and unrestricted adversary that controls all but one server and one client. Specifically, our protocol guarantees that such a powerful adversary only learns the histogram of all of the queries and nothing else, and this histogram is differentially private. Our protocol also provides integrity guarantees that ensure that any user only accepts responses that are correct and correspond to the database as agreed upon by the servers. For simplicity, let's consider the case with 2 users and 2 servers. And let's say the pink user wants to query row number 3, and the gray user wants to query row number 1. In the very first step of the protocol, each user samples random masks that, when XORed together, reconstruct to 0. The user is going to sample 1 mask per server, in addition to 1 extra mask that it stores locally for later use. We'll use these masks to hide the responses while they're processed by the servers. And in this figure, we show all these masks as puzzle pieces. Then each user onion encrypts their queries and their masks using the server's public keys. Each layer in this onion cipher corresponds to a single server and contains the mask associated with that server. And additionally, the deepest layer also contains the query and is associated with the very last server in this chain. The first server collects all these onion ciphers from all the different users, forming a batch of queries. Again, this batching is required for amortization. The server decrypts the outer layer of every onion. Note that while it can decrypt the outer layer, it can't decrypt the inner layers because it doesn't possess the right private key. Right? So the server can't learn the queries, the contents of any of these queries. Now, the decryption of the outer layer provides the server with 2 outputs: the masks, which it will store for later use, and the inner layer of the cipher. Then the server samples noise from a select distribution. We carefully select this distribution to ensure that the overall histogram that includes both the real users from real user queries and the queries that are noise, both of these together, the histogram is differentially private. When sampling the noise, the server also samples random masks and encrypts them with the noise queries to ensure that real queries and noise queries are indistinguishable. Note that the amount of noise we add here is linear in the size of the database. It's independent of the number of input queries and users. This is important because it means that the noise becomes relatively smaller in applications with many queries, and thus amortizes to a small constant overhead per query. Then the server shuffles all these queries together, and this hides and conceals which of the queries are noise, which of them are real. And the server sends this shuffled result to the next server. Now, the last server in the chain decrypts every element, revealing the contents of every query and the mask. Crucially, the server cannot tell which user is the origin or source of the decrypted query, and it cannot even tell whether that decrypted query is real or noise. So the only thing that this server learns is the overall distribution or histogram, which is differentially private. The last server looks up each decrypted query in the database, finding the associated response. We cannot just send these responses back to the users in plain text format because that leaks information about their queries. So instead, we will XOR the responses with the masks to hide them. The last server sends the masked responses back to the previous server, and that server deshuffles them and removes the responses that correspond to the noise it added earlier on. Then the server XORs the remaining responses with the masks it previously stored and sends them back to the prospective users. And finally, each user applies its own mask and reconstructs the desired output. Now, what I just showed you is a simplified construction that performs all the operations online, including the expensive onion encryption and decryption operations. In the full construction in the paper, we only use a cheap secret sharing scheme online rather than onion encryption, and we use onion encryption only offline to install the required secret shares at the servers so that the servers can use these shares online. Compared to previous work, our offline stage is in a sense flipped. Rather than the users receiving a hint from the servers, the users in our protocol anonymously store hints, in this case secret shares, on the servers. For this to work, the secret sharing scheme needs to have certain security properties similar to onion encryption. In particular, the scheme must be incremental, where the query is reconstructed one server at a time in the chain. And this is similar to the onioning aspect of onion encryption. It also requires that the scheme be non-malleable and resilient against adversaries that may maliciously modify shares. And this is similar to CCA security in onion encryption. To the best of our knowledge, this is the first secret sharing scheme that satisfies both properties. All right, now it's time to look at the performance of our new protocol. We'll look at the same experiment from earlier in the talk. The x-axis is the number of queries in a batch, and the y-axis is the total completion time online in seconds. A main observation here is that our protocol handles the batch of Q queries in Q plus n rather than in Q times square root n. For batches with few queries, you can see that our runtime is basically constant. This is because the amount of noise queries overwhelms and dominates the system and is far greater than the few real queries made by users in this case. This means that per query, amortization isn't very effective, and we're performing work linear in the database for each of these queries. And this is also confirmed by the fact that checklist outperforms our protocol. However, as the batch size increases, our protocol becomes dominated by real queries, and the fraction of noise queries becomes smaller and smaller. So our amortized work per query now becomes an increasingly smaller constant, and we increasingly outperform checklists due to this amortization. At 1 billion queries, which is roughly the scale of our software dependencies example, we observe that the cost of our protocol is 2 orders of magnitude lower than checklist. In our paper, we discuss another application with mobile app stores. We show more experiments, including comparisons to other peer protocols, and we show the effects of the batch size on our throughput and latency. And we also spell out the secret sharing scheme, which I only highlighted, and we formalize its properties. In conclusion, we presented DP-Peer, a novel differentially private peer protocol for applications with many queries. Our protocol exhibits constant amortized computation and communication complexities and concrete performance boosts up to 2 orders of magnitude over existing work. And this makes peer suitable for applications domain that were previously understudied or thought to be impractical. Thank you.